the basic types that you can use in the C language. And we had gotten to the floating point types. Basically, so with the floating point types, they're basically the same as they are in Java, right? So you have float and double. You also have a long double, but that's not commonly used. For the floating point types, if you want to print them, you're using these conversions %f, %e, and %g. Right? So remember, %f is the standard, I guess, conversion to print a floating point number. %e gives you your scientific notation. %g chooses between %f or %e, depending on the magnitude of the number. Right? And so when you print out the numbers here, let me print out pi here. Right? You end up with the following. Right? So remember that %f and e default to 6 digits of precision. %g defaults to a total. %f and %e default to 6 digits of precision after the decimal place. %g defaults to a total of 6 digits of precision. I guess, so one thing you never get told, and I don't know how it works either, is how you actually, or how the computer or how C actually generates the string representation of a number. Right? So we take for granted that you can just print a floating point value, right? Especially in Python or in Java. Right? You just print values willy-nilly all over the place. In C, you can see that there's an issue now. Right? So you can see that there's this issue of how many decimal points, how many digits of precision do you actually print? Right? So for example, if I strip off all of these digits after pi, right, there are no significant digits after the 3. Right? But %f and e still print out 6 digits of precision. Right? %g does something a little bit more intelligent, right? And it only prints out the 3 because there are no other remaining digits of precision. Right? And so you can start to see that there's this issue of how do you actually print a floating point number? And the answer is it's surprisingly hard. Right? So how do you print a floating point number? So it turns out how to do this accurately and efficiently is very hard. In fact, it's so hard that when the specification for the floating point numbers was finalized, or I guess the first version was finalized, we still didn't know how to do it. So when the first draft of the IEEE spec was 1985. So in 1985, we didn't know how to print out floating point numbers accurately and efficiently. And so you can kind of guess, there's actually, if you actually read this web page here, so where's the link? The link is up there. If you Google it, you can find it pretty quickly. So if you're interested in how this is actually done, there's a bunch of links in this web page that tell you all the gory details about how to print, on the issues related to printing out floating point numbers. Right? For a number like pi, can I undo this? Control, yes. Right? It's not clear how many digits of precision you'd want to print out in this number. Right? So in C, you can specify, well, the user can specify, the programmer can specify how many digits to print. Right? And so the number of digits to print, you would specify using dot something, dot integer number in front of the conversion specifier. Right? Dot 1 means 1 digit of precision. Dot 10 would mean 10. And dot 100 will do up to 100 digits of precision. If you use F here, you will get 100 digits. Right? But if you use %g, you won't. So %g knows to stop when it starts to see this, when it realizes there are no more remaining significant digits. Right? And so now you can see that you have another problem, is that you're not even guaranteed what the output is when you print a floating point number. Right? The two different conversions behave differently when you print the number. All right, so just keep those things in mind as we move forward. So C has this notion of a what's called a const qualifier. Right? So you can make a variable, and then you can declare that variable to be const. Right? And so when you make a const variable, that marks the variable as being unassignable or read-only. Right? So it's not it's different than final in Java, right? So final in Java means you can give a variable, variable a value once, right? But you can do it whenever you want to, right? As long as the variable's in scope, right? In C, when you declare a const variable, it becomes read-only. So if you don't initialize it, you can't set its value. So you're almost always going to initialize a const variable when you declare it. Right, so where to go? Right, so here, I'm using the value pi again, right? And I'm going to declare it to be const, right? You just put const in front of the variable type, right? And so that says that pi is now a read-only variable, right? So in other words, pi is forever the value 3.14, blah, 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 blah. Right? If you run the program, it just prints out, oops, sorry. Oh, well, that sucks. How do I get this to, this actually is a fun problem. So, okay, so the math header file, this includes this is the header file that declares the basic math functions that are in the C library. Right? It's similar to Java lang.math. So there's the function cosine, there's the function sine that I want to use, right? Looks like when you're running this in Jupyter, although I didn't know this was a problem. Okay, so it looks like when you're running this in Jupyter, Jupyter's not happy with it. You end up with this symbol lookup error here, undefined symbol cosine. I guess this is a good time to show you how to resolve this. Okay, so I'm going to go directly to the source code now. So there's const, right? If you compile this program, the way I showed you how to do it before, so GCC -o, like that, right? It also complains of the same error, right? So it complains there's an undefined reference to cosine, right? Now the reason this is happening is because, if we look at the source code again, const, like that, right? That function cosine is declared in math.h. Right? So in math.h, there's a line that says the function cosine exists somewhere, right? But the implementation of cosine is not in math.h, it's somewhere else, right? So it turns out that the implementation of cosine is in the math library. So there's a precompiled library that contains the object code for the math.c, and the definition of cosine is in there. So that means we need to link to that library. Normally, you don't have to link to any of the standard libraries. The exception is math. So when you compile this thing, right, you have to tell the compiler to link to the math library. So the way you do that is you write -l and then m. So m's for the math library. Yep.
For me, it works fine.
Yeah, it probably works for some versions of Jupyter and it won't in others. Yeah. So I'm just showing you how you would actually resolve this. So now when you compile it, everything's fine, right? And now if I run it, you also get that, right? So now you get the output 0.806, 0.5. All right, so that's when if you're using the math library, in most cases you have to link to it. Oddly enough, there are some instances when you don't, but never mind. Okay, so we're talking about const here. So what I really wanted to be able to do is to uncomment that line there and try to run it now. Okay, so now you get the error, right? So now you get a compiler. It says assignment of a read-only variable pi, right? So you get this error here because pi is read-only, right? You can't assign a value to it. You can't write a value into it. Right? So if you declare a variable to be const, or a parameter to be const, you can't change that variable. So if you want to make a constant, and you want to make sure that it's constant, right, then you can declare it to be const. The other place you'll see const a lot is as a parameter to a function. Do I have one here somewhere? I don't have a handy one here. Many functions will declare one or more of their arguments to be or parameters to be const. And that indicates to the caller of the function that the function promises not to change those values. Right? So for example, if you pass an array to a function and the array is declared to be const, the function is promising not to change the elements in your array. Right? But we'll see examples of those later on in the course. Okay, so the type void in C on its own means cannot hold any value. Right? And so in the main function here, right, it shows up in the parameter list to indicate that there are no parameters in this function. If you use it as a return value, that means that the function does not return any value. Right? The more interesting use of void is when you have a pointer to void. And so we'll talk about pointers in a little bit. So pointers to void turn out to be enormously useful in the language. We'll see examples of this later on. You can't ask for the size of void. That turns out to be an error. Right? But that kind of makes sense because void means can't hold any value. Right? And size of is defined so that everything is measured in units of car. Right? So the smallest thing that size of can return is 1. Okay, so arrays in C. So this is where things start to become very different compared to the languages you've learned already. Right? So there are similarities between arrays in C and arrays in Java. Right? So for example, arrays, they both represent a contiguous sequence of objects all having the same type. Right? So an array of int means you've got a bunch of ints. Contiguous means that the memory they occupy, each element is laid out in memory one after another. Right? So there's an int, and then right after it there's an int, and then right after that there's an int, and so on and so on and so forth. Right? So contiguous chunk of memory means one block of memory for the array. Just like in Java, the capacity of the array never changes during the lifetime of the array. Right? If you want to expand an array, you can't. Right? Or if you want to shrink an array, you cannot. What you have to do is you have to make a new array. Copy the elements from the old array into the new array, and then you have an array of different size. Right? So there's no way to change the size of an array once you create it. Just like in Java, the type of the array involves the type of the element. Right? So if you have an array of int, then the word int is going to appear when you declare the array. And just like in Java, you're going to use square brackets to access elements of the array, right? And you access them in exactly the same way. The zero-based index, no negative indexes. There are many important differences. So in Java, if you have an array variable, you can assign another array to that variable, right? So int square bracket x equals some array. Right? Then at some later point, you can say x equals some other array in Java. You can't do that in C. Right? So if you have a variable whose type is an array, you can't assign to it. Right? You can assign to the elements of the array, but you can't assign a new array to that variable. Right? So there has to be a way to get around this problem because obviously you're going to want, if you change the size of an array and you're storing it in a variable somewhere, you're going to want to reassign that variable to point to another array. There is a way to do it. We'll see how to do it later on. The capacity of the array, if known. Oh, right. So in C, you can declare the capacity of the array. You can use the capacity of the array as part of the declaration if you want to, if you happen to know what it is ahead of time. So I'll give you an example of that in a minute. Now this is the big difference here. This is the important difference for right now. Right? So in languages like Java or Python, if you try to access an element of a list or an array and the index is invalid, you are immediately told that there's a problem. Right? So in other words, in Java, you get an index out of bounds exception and your program normally crashes. Right? In Python, you get some sort of exception raised. Right? In C, you do not. Right? So you can make an array of size 5 and then try to access the 100th element of the array. It may work. You may get something, in other words, right? So you might get some value. You might get an error. But you have no idea what's going to happen. Right? So there's no bounds checking. If you're off by 1, it's very easy to not be able to find that error until something strange happens. Right? So in other words, if you go 1 past the end of the array, it might look like your code's working until it doesn't. Right? So you have to be very careful when you're using indexes with arrays to make sure your indexes are always valid. Here's another big one. If you want to write a function that takes an array as input or returns as an array as output, you can't actually do so because of the way that arrays behave in the language. So the way that arrays behave in C is that your array actually degrades to something else. So it actually gets converted to something else when it's a parameter of a function or when you try to return it from a function. And so we'll see exactly what happens in a later lecture, right? And because of that, it's actually impossible to return an array from a function, right? So if you write a function and it says you try to return an array from that function, the compiler will complain. You have to return something else, right? And we'll see what the something else is later on. Okay, so creating arrays are not particularly different than creating arrays in Java. It's slightly different. So here, I'm making an array of int, right? So int x and then square brackets, right? Indicates that this x is an array of 3 ints, right? In Java, most Java programmers would write that as int square bracket x, and then they would say new int 3, right? In C, there is no new operator. So this actually does make an array of length 3. Right? You don't have to write the new int blah, 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 blah that you'd have to do in Java. Right? That really does make an array of length 3. Once you have that array, you can go ahead and assign values to the array. Right? So x0 is 1, so the first element of the array is 1, and so on and so forth. If you want to access an element of the array, it's just use an index and the square brackets. Right? So to print the elements of this array, I can use printf with %d, right? \n, so a new line after each element. And so this will print out the contents of the array on 3 separate lines, like so. Right? So using the array is not any different than using the array in Java. All right, so remember size of from the last lecture. So size of tells you how much memory an object occupies. So you can ask for the size of an array. Right? And what does that return? That returns the amount of memory in bytes that's used by the entire array. Right? And so what's that equal to? The capacity of the array times the size of each element in the array. Right? So the size of this array here is 3 times the size of int, whatever that happens to be on your computer. Right? Because we need space for 3 ints. So for example, right here, right, same code as before. There, I'm going to print out the what's returned by size of. And then on the next line, I'm going to print the capacity or the number of elements that are in the array. Right? So the size of x gives you 12. Right? That's equal to 3 times the size of int. So if you divide by size of int, right, you get back the capacity or the maximum number of elements that you can store in the array. Right? So that gives you back 3. Right? Now that I've told you about that, you should forget about it. Okay? So strange, but I'm going to tell you don't use size of when you have an array. All right? That's what this big yellow box is for. Okay, so now that you know what size of does if you pass in an array, you should forget about what it actually does if you pass it a size of array. If you pass it an array. Right? So you should never use size of to get the size of an array. Number one, because you already know the size of the array. Right? In this function main, I know that the size of x is 3. Sorry, the number of elements in x is 3. Right? So I know its capacity. I know its type. So I can easily compute its size. Right? It's just 3 times the size of int. Right? Okay, so why am I telling you not to ever use size of? It's because a lot of new programmers, when they're starting to write code for the first time, they'll write a function. One of its parameters will be an array. Right? They want to know how many elements are in the array, so they will write size of and then the name of the array inside their function. The problem is when you have a parameter that's an array, size of does not tell you the size of the array. It tells you the size of a pointer, which is always 8 on my computer. right? And that's because of the way that arrays behave when you transfer them to functions, right? The array doesn't remain an array anymore. It degrades into something else, right? So if you're inside of a function that's passed an array as an argument, then the function actually receives a pointer to the first element of the array, right? And I'm going to tell you what pointers are in a bit, right? So using size of actually returns the size of the pointer. It doesn't tell you the size of the array, right? So forget that I ever told you what size of array does, right? You're not going to want to use it in any actual circumstance. All right, one more time, I'm going to emphasize that there is no array bounds checking in C, right? And you are really going to miss this fact when you start programming in C, right? Because it's very common for all programmers to make indexing errors when they're using arrays or lists, right? If you use an invalid index, right, then you end up with what's called undefined behavior in C. You should remember this phrase, undefined behavior, because it appears everywhere in the C language standard, right? Undefined behavior literally means anything can happen, right? So if you use an invalid index in your program, anything can happen to your program. It might crash, it might appear to work, it might appear not to work, right? But you have no idea what's going to happen, right? If you're lucky, the program crashes. Right? If you're unlucky, right, then if you write into that index, you're going to write into a location in memory that you shouldn't be writing into, right? So if you're really unlucky, you write over one of your other objects in your program, right? So you just writes over the memory that's there, and your other object now becomes corrupted, right? And now when you try to debug your program, when you look at the other object, you say, what the heck happened to my other object, right? Where did this happen from? Right? And it's because you indexed some array from somewhere, who knows where, right? And it just so happened that it ended up overwriting your other object when you incorrectly indexed into that array, right? So here's an example right here. I'm going to make array 1. It has 5 minus 9s in it, right? I'm going to print out the first element of that array. You should get minus 9, right? I'm now going to make an array of size 3, right? I'm going to write into the first 3 elements, and then I'm going to write into the 4th, which doesn't exist in this array, right? I'm pretty sure when I run this program, I don't get an error, right? I'm going to print the size of x, right? That should be 12, right? I'm going to print the capacity of x. That should be 3. And then I'm going to print out that first element of that first array again, right? And so let's see what happens. So array 0 is minus 9, right? The size of x is in fact 12, good. The capacity is in fact 3, good. The first element of my first array is now 4, right? In other words, that write right there, right? So that write into x, right, at element number 3, or element indexed at 3, sorry, actually writes into that value right there, right? There's no error, right? And you don't know that there's a problem until you actually look at the elements that's in array 1, right? So the compiler doesn't help you, the runtime doesn't help you, nothing helps you, right? You've made a mistake in your program, and the C language is going to punish you for it, right? And whether or not you know you were punished, you don't realize until something has happened. All right, so we're going to come back to arrays in a later notebook, because the topic of using arrays is a much larger topic than I want to cover here. Strings. So most of you, yeah, sorry, back.
Just in the program code there.
Yep.
What is the difference between like printing with %LD or %P?
So here. So size of returns an unsigned integer, and it turns out it returns an unsigned long integer on my computer, right? So if you just use if you just use D here, the compiler should complain. It doesn't fail to compile, it just complains, right? So it says here, there's a warning, right? %d expects an argument of type int or smaller, right? But instead, it gets an argument of type long unsigned int, right? And so when printf goes to print the value, it's going to assume that this thing here is actually an int, right? Because you told it it's an int. That's what the %d means, right? So if the number is small enough, so in other words, if it fits inside the value fits within the range of int, it will correctly print the value, right? So this actually does run, right? And you get the correct value. If it happens to be the case that it doesn't fit inside of an int, when it prints the value, you'll get the wrong value, right? That's all it means, right? So it's not like Java, right, or Python that automatically figures out what is the size of the thing that's being printed, right? And C, you have to tell it, and if you tell it the wrong thing, again, the language is going to punish you for it at some point. Okay, strings. So again, here's something else. So in Python, in Java, when we teach you those languages, often we print a bunch of stuff out to the console. It's probably less common in C that you print stuff out to the console. One of the reasons it's less common is because C doesn't actually have a proper string type, right? So in C, strings are just arrays, right? So they're literally arrays of car, right? There's no dedicated string type in C, right? Furthermore, strings in C, not only are they arrays of car, but it's assumed that the last character in the sequence is the number 0, not the printable number 0, literally the value 0, right? And so that's called the null terminator, or the null character constant, right? As a character, you write it as \0, right? So as a car literal, it's \0, right? As a numeric value, it's just the numeric value 0, right? Which is different than the car is not equal to, is not equal to the number 0, right? So in C and pretty much in Java and Python, right, the character 0 does not have the numeric value of 0, right? So you want the numeric value of 0 to indicate the end of the string, right? So if you have a string of length 8, in memory it actually takes up 9 characters of memory, because you need to include that null terminator at the end. Right? So string literals look the same as they do in Java, so they're double quoted, like that. Right? Now, because strings are just arrays of characters, right? When you want a string, you end up writing something like that, right? So car string, square bracket, says that string is an array of car, right? And in this case, it contains the characters CISC220 \0, right? So there actually is a \0 on the end of this string literal, right? The compiler puts it there for you. You don't have to put it in yourself, right? So if you print that string, not surprisingly, you get CISC220. All right, now because of the fact that there's a \0 hanging off the end of that string, that means there's a difference between the size of the array that holds the string and the length of the string, right? So the length of the string, in this case here, is 7, right? 7 characters in that string. The capacity of that array is actually 8, right? Because of the extra null terminator, right? The \0 that's hanging off the end. So again, I'm going to use size of again, even though I told you not to, right? So here, we've got an array of length 100, right? I'm going to store the characters CISC220 in that array, right? I'm going to print the capacity of the array, which should be 100, right? And I'm going to print the length of the array, which in this case is going to be 7, right? So you can store a string in an array that has excess capacity. Right? The first few elements of that array will be CISC220. The next character will be \0. Everything else in that array could be anything because the memory is not initialized when you make an array. right? So the other 92 characters in that array could be anything, right? You don't know what they are. So in a little program like this, they're almost certainly 0. But in a larger program where you're constantly allocating and deallocating memory, they're probably not zeros. When you ask for the length of string length. String length is the function that you use to ask for the length of a string, right? It's defined in the header file string.h. All of the common string handling functions are in string.h. All right, now, because strings are just simple arrays, it's very easy to create a string that is missing the null terminator. Right. Why did I use malloc? That's interesting. All right, well, let's use malloc. Okay, so we're going to see more of malloc later on. Malloc is one of the C functions that you use to ask for memory. Right? So malloc1 asks for 1 character of memory. Right? And I'm going to store that in this thing that's called a pointer, which I haven't told you about yet, but we'll get to that in a minute. Right? So that thing there returns what's called a pointer to 1 character of memory. Right? Now I can use that pointer and treat it as though it were an array. Right? Again, I'll tell you more about pointers. I'm not sure today or in the next lecture. Right? But I can treat that pointer as though it were actually an array. Right? So I can store the character C in that array. Right? I don't know why I used malloc here. I could have done this another way. Anyway, it's fine. Right? So there's my string. Well, there's my alleged string. Right? It's got the character C in it. If I ask it for its length, right? Let's see what happens. Oh, we get length 1. That's awesome. That's great, right? Why did that happen? 2? Still 1? This is a bad example. Sorry. Why did I write this example? Still 1. Oh, okay. Well, anyway, all right. So here, in this particular case, we're always getting the correct string length. Right? We're always getting 1, and there really is only 1 character in this string, right? But this isn't guaranteed to be the case, right? So in other words, it's possible that you run this code again. Probably not as simple, probably not as a small program like this, but you end up getting the wrong string length. And that's because you haven't put in the null terminator specifically, right? So when you are creating a string, you have to, if you're creating a string manually, you have to remember to stick in that null terminator. If you don't, then there is a possibility that you end up with an incorrect string. I have to fix this example. There's something funny about this example. Is it here? It is here. Let's see what happens if I run it from the console. Oh, still get 1. Okay. Okay, so I'm going to revisit this and try to remember exactly why I did this example. But the fact that there is no null terminator on this string means that this may not necessarily be a string of length 3. Sorry, a string of length 1. String of length. Okay, so we're going to talk about strings in greater detail later on as well, because you need to know about all of the string handling functions in order to be able to use them, in any meaningful way. Structures in C. So a structure in C is the closest thing that C has to a Java class, and it's not very close. Right? So a structure in C is what's called a composite type in C. And all that means is a structure in C is made up of a bunch of other variables. Right? And so you can group a bunch of variables that are probably related somehow into one chunk of memory. Right? So the variables are called members, and you can access them by by asking the structure object for the individual members. It looks a lot like Java. So it sort of resembles a Java class where all of your fields are public, right? There's no methods, there's no constructors, right? And so what a structure lets you do is it effectively lets you create a primitive, it effectively lets you create a new type in C, right? So the way you declare a structure is as follows. It's struct, there's the name of the structure, and then your members just get listed inside the structure individually. So for example, right, there's a structure there that implements a two-dimensional point, right? So it's a point that has an x and a y coordinate. The name of the type that you've just created is struct point 2. So the word struct is part of the type name. Right. You can initialize a structure just like you initialize an array. Right? So if I want to make an object, a variable p, right, whose type is struct point 2, right, then I can initialize the x and the y coordinates using the braces, right? So just like you would do in Java with an array. Right? So in this case, px is 0.1, py is 0.2. Right? If I want to get to the x and y values of the structure, you just use the dot notation. Right? So there's my structure up here. There's a structure variable right there. Right? If I want to get the x value of the structure, I just write p.x. Right? If I want to get the y value of the structure, I just write p.y. Right? If you want to change them, well, you just write p.x equals something, and you just write p.y equals something. Right? p.x is a double, right? And p.y is a double. So if you run this, not surprisingly, the first time you print out the point, you get 0.1 and 0.2. Right? And the second time you print out the point after changing the coordinates, right, you get 100 and 200. So in C, you can assign a structure object to another structure object. Right? The way it works in C is that you copy all of the memory from one structure into the new variable. Right? So here, there's P, right? Its coordinates are 0.1 and 0.2. Right? Here's Q. Its coordinates are you don't know and you don't know. Right? So you literally don't know. It could be anything. Right? But the coordinates are there. So there is a q.x and there is a q.y. You just don't know what they are. Right? You can do assignment with structures like that. Right? And so that, you can think of this literally as being q.x equals p.x and then q.y equals p.y. Whether the compiler actually does that or not is a separate story, right? But that's effectively what happens. Right? You get element by element or member by member copying. Right? So if you print out p and q, you're going to get the same thing. Right? So when I print out p, I get 0.1 and 0.2. When I print out q, I get 0.1 and 0.2. If I change p, px to 100, and if I change qy to 200, right, then px changes, right? So px is 100 now. Py doesn't change, right? Qx is still 0.1, so it didn't change when I assigned to px, right? But qy changes now, right? And so these are two, p and q are two independent objects here, right? They're two independent variables. If you assign like that, they're still independent variables. Right? So it's not like in Java or in Python where you have aliasing happening, right? These aren't references, in other words. All right, so those are the major types that we're going to be using in this course. Sorry. Right. All right. Any questions so far? So we're going to go back, of course, and look at arrays in more detail. We're going to look at strings in more detail. We're going to look at structures in more detail. Right. So for now, let's go and look at the scope and lifetime of objects. Okay, so you guys, you all know about scope from Java, right? So the scope of a variable is the part of your program where you can actually use that variable name. right? And so it's the same thing in C, right? And in C, the scoping rules are almost the same as they are in Java, right? So C and Java both use braces to indicate blocks of code. So the scoping rules are similar in the two languages. There are some differences, of course. Now, something that we never talk about in 121 or 124 is the lifetime of objects, right? Because you normally don't care, right? The languages take care of, you can make an object, but the languages take care of getting rid of the objects, right? In C, that's no longer the case all the time, right? And so in C, the lifetime of an object becomes important because the programmer can control the lifetime of an object. You can't do that in the other two languages. All right, so scope. So in C, there's 4 types of scope. There's something called file scope. There's something called block scope. So block scope you know about because it's the same thing as in Java. Right? Function prototype scope, which is new, and then function scope, which is also new. And function scope is not relevant in this course. Right? So we only really care about the first 3. And we really only care about the first 2 because the third one is somewhat uncommon. Right, so what's file scope? So you know that in Java, if you make a class, everything's inside of a class in Java. Right? There's no way to declare a variable outside of a class. Right? In C, you can declare a variable pretty much anywhere you want. Right? So if I make a program called scope.c, right? I can declare a variable outside of a function, right? And so J is a variable that has file scope, right? So in other words, it's a variable that's declared outside of a function, right? There's a variable J, so that's at file scope. Notice there's a J inside the function f, right? So that J is different from that J there. F has a parameter called I. Inside this for loop, there's another I, right? So that I is different from that I, right? Inside the for loop, there's also another variable J, right? That J is different from that J and is different from that J, right? To figure out which J is being used, you need to know about the scoping rules. Okay, so we're interested in file scope here, right? Where's K? Oh, K is also down here. So later on in the program, after the first function, there's a variable called K. Right? K is not inside of a function, so it has file scope. Right? Do I ever print it out? Oh, I never printed out. Okay. Now, notice that K is declared here. Right? I have a function up here. Right? In this particular program, if I try to use K up here, it won't work, right? Because K is declared here, right? And so the order in which you declare things matters, right? K is declared here, so what that means is K is usable at this point onwards, right? The file scope variable J is usable at this point onwards, right? F comes before K. So if I try to use K inside of F, right, the compiler is going to complain. Right there. Right? So it says in the function F, K is undeclared. Right? First use inside this function. So it's complaining it doesn't know what K is. Right? Even though K has file scope. Right? So if you're in this situation, you can move K. Put it up here. Oh, sorry. Okay, and now the compiler's happy, right? Or you can move the function to be below the declaration of K, either one. Right? All right, so block scope. So block scope you know about, right? So braces denote blocks of code, right? If an identifier is declared inside of a block, right, or in a parameter list, then that variable has what's called block scope. Right, so back up here, I has block scope, J has block scope, that I has block scope, that J has block scope. Right? This K is still file scope. Okay, so an identifier or a name that has block scope, it becomes usable at the point where it's declared and within that same block, right? So back up here, right? That variable I is usable anywhere inside of here, right? Now, which version of I you get depends on the other, depends on if there's a variable called I in another block, right? So this variable called j is usable from this point to there, right? And this variable I, right, is usable inside of its block, so it's usable here. Right? And similarly with the variable j, right? So j is usable from this point to this point, right? Which variable you get, it depends on, is the closest variable to the block that you're in, right? So here I'm using I to print out the value of I, right? So the version of I that I get is this I that's right here, right? The I that was declared for that block, right? I'm not getting the parameter I up here, right? J, I'm also using inside of this block, right? So the version I of j that I get is the variable j that's declared inside of this block, right? Whose value is always 2, right? So even though j here, right, is usable all through here, right? The value of j that gets used inside of here is the variable j that's declared inside of the block itself, right? So in other words, that j right there is actually that j right there. Yes?
What if you wanted to get the value of the other j?
There's no way to do it. No, there's no way to do it. Yeah. So don't repeat your variable names is basically the rule. Yes, that's correct. So it's legal, but often confusing to declare identifiers with the same name in different scopes. Right? So this example is intentionally confusing. Right? You should generally avoid doing stuff like this. And so what happens here is when you declare a variable called j inside of a block, right, that j that I just declared hides every other j. Right? So it hides that j that is also in scope, and it hides that j that is also in scope at that point. Right? And there's no way to get around it. So there's no way to unhide the other j's. The exact same thing happens in Java as well. Right? Okay, so function prototype scope is worth talking about because it's very quick. And, oh no, actually it's not. It's 120, so I should stop there. So we'll finish talking about scope in the next lecture, and then what is the next lecture going to be? Scope declarations. So I guess we're going to be using variables in the next lecture.